Welcome to this fourth module. So, in this module we will try and do some problems originating from the damped oscillator. So, a very quick review before we plunge into the problems. So, as usual we begin with the equations of motion and they are here, and just to remind you, gamma is the dissipation coefficient and S is the stiffness constant, and in general you can obtain solutions for this. We spent last 3 modules doing that, and here is the general solution. And 2 other things that we will be needing are this omega 1, which is the frequency of the damped oscillator, and in fact this quantity here is omega 0 square, which is the natural frequency of the undamped oscillator. So, I can write this as omega 0 square minus gamma square by 4 m square. And we also learnt about the Q factor or the Q value, which is m omega 0 by gamma. So, this is the approximate value, which is valid for when the dissipation is small. So, with this background, let us quickly get into the first problem. First problem is among the simplest. For a damped harmonic oscillator, we are given that omega 0 square minus omega 1 square is equal to this value 10 power minus 6 multiplied by omega 0 square. We need to find the Q factor. So, all we need is the formula that is given here, and we just rearrange this equation. Omega 0 square minus omega 1 square will be equal to gamma square by 4 m square, and we are told that this quantity here is simply equal to 10 power minus 6 into omega 0 square, that is gamma square by 4 m square. So, if I bring omega 0 square down here, I will have gamma square by 4 m square omega 0 square is equal to 10 power minus 6. Therefore, the quantity I have here is 1 over 4, and this is simply q square in the denominator. Therefore, q square will be equal to 1 by 4 into 10 power minus 6, which is equal to 10 power 6 divided by 4. So, Q factor is 10 power 3 divided by 4, that is 1000 divided by 4 equal to 250. And remember that Q is dimensionless quantity. So, it is a ratio of 2 energies, hence it has no dimensions or no units. In the second problem, the question is amplitude of a damped oscillator decreases by 5% during each oscillatory cycle. Find the percentage of mechanical energy of the oscillator that is lost in each cycle. So, remember that energy is simply square of the amplitude for our purposes. To do this problem, what we need is the ratio of the amplitudes. A0 by A1 is e power delta. So, hope you remember the definition of delta that we had, which was gamma tau prime divided by 2m, where tau prime is the time period of the damped oscillator. Now, A0 is the initial amplitude of the damped oscillator, and the statement here says that after one period it decreases by 5%, in which case A1 will simply be equal to 0.95 A0, and that is equal to e power delta. So, A0 and A0 will cancel out, and I will get e power minus delta is equal to 0.95. So, if we take logarithm on both sides, we will get delta to be equal to 0.051. You can do this calculation yourself with the calculator and check that this is the value of delta. Now, we know what is the value of delta, which means that we know that this is equal to 0.051. I also know that tau prime is equal to 2 pi by omega 1, and as usual we are going to assume that the damping is sufficiently small, so that this is approximately equal to 2 pi by omega 0. So, now if I substitute this in the value of delta, I will get delta is equal to gamma by 2 m into 2 pi by omega 0. So, 2 and 2 will cancel out. I will get pi into gamma by m omega 0. So, this tells me that delta here is equal to pi into pi divided by q. So, if you remember, m omega 0 by gamma is the q factor. From this I can rewrite this equation as q is equal to pi by delta. We know that q is equal to energy stored divided by the energy lost in one cycle. So, what we are interested in is this energy lost per cycle, and this is equal to pi by delta. So, let me say that energy stored initially is E 0 and energy lost is some fraction of it, which I will call q E 0. So, with this in place, all I need to do is to plug in these two in this equation, both E 0 and q times E 0. If I do that, I am going to get the following. This will imply that again E 0 and E 0 will cancel out, and it tells me that q is equal to delta by pi. If I substitute the value for delta, I can find out the value of q. So, delta is 0.051 divided by pi is approximately 3.141. So, this will give me a number which is 0.0081. So, this implies that about 0.8% of the energy is lost per cycle. So, that is the answer to this question. So, in the third problem, the question is show that the fractional change in natural frequency, which is stiffness constant divided by mass for a damped simple harmonic oscillator, is approximately equal to 1 by q square. So, the starting point to solve this problem is we should be able to relate the frequency of the damped oscillator to the frequency of the undamped oscillator. So, from here we just need to do some few simple manipulations. The starting point for this is the formula which we had seen before. So, we will just slightly rearrange this equation, and if I take square root, I will get omega by omega 0 is 1 minus gamma square by 4 m square omega square whole to the power half. So, here is where we will do a binomial approximation, and if I do the binomial approximation, I will get 1 minus gamma square by 8 m square omega square. So, note that if x is small for a function like this, binomial approximation would mean that 1 plus q x. So, this is the case when you terminate the binomial approximation at the end of the first term, which is exactly what I have done here. And from here we recognize that m omega 0 by gamma is q, and we can take 1 on the other side. If we do all that, we should be able to get omega 1 minus omega 0 divided by omega 0 is equal to minus 1 by 8 q square. Notice that q is equal to m omega 0 by gamma. And now with a slight rearrangement, omega 0 minus omega 1 by omega 0, which is the fractional change in the natural frequency, would be equal to 1 by 8 q square. So, this is the answer that is required, and the approximation here was done here applying binomial approximation. Let us start with the next problem. In this case, a mass is subjected to a dissipative force equal to minus gamma times v, where v is the velocity, but it does not have a restoring force term. In other words, it does not have a Sx term. So, we need to solve this equation and find the displacement as a function of time. So, let us do this. So, normally this is your equation of motion. For the damped oscillator. However, in this case we are told that this term does not exist. So, the effectively the equation is m x double dot plus is equal to 0, and we need to find solutions, which means I need to find x of t. That is the question. So, the method of solution is same technique as the one that we adopted for solving the dissipative harmonic oscillator. So, let us assume solution x of t to be a, which is a constant, e power alpha t, and we will determine this alpha in a while. X dot of t would be a alpha e power alpha t, x double dot of t would be a alpha square e power alpha t. Now, we need to simply substitute these things back in this equation. If I do that, I will have m into a alpha square e power alpha t plus gamma a alpha e power alpha t is equal to 0. I can take e power alpha t outside. For this equation to hold identically, and e power alpha t is not 0 for arbitrary values of alpha and t. Hence, the condition is that this quantity is equal to 0, and you see that there is a in both the terms of this equation, which can also be removed. So, I will have m alpha square plus gamma alpha is equal to 0, and I can, for example, divide throughout by m, in which case it will be, if I take alpha out, I will have alpha plus gamma by m equal to 0. So, the solutions are easy, either alpha is equal to 0 or alpha is equal to minus gamma by m. So, these are the two possible values of alpha. I can now plug this back into the equation that I assume a e power alpha t. If I take alpha to be equal to 0, x of t would be equal to a, which is a constant. On the other hand, if alpha is equal to minus gamma by m, x of t would be a e power minus gamma by m into t. So, these are two linearly independent equations. These are two linearly independent solutions. You cannot obtain one from the other just by multiplying a constant. So, there is one constant which is a, which is already there in this equation. So, the general solution for displacement as a function of time would be e power this one. Because we were solving a second order differential equation, which is this, we should have two independent constants, and that is satisfied by this form of the solution. If we had some initial conditions, we can plug in that initial condition and reduce one of the constants. For instance, let us say that I know that x dot of 0, velocity at time 0 is equal to some v 0. So, in that case one of the constants can be eliminated as follows. I need to find first x dot of t. From here x dot of t would be b into minus gamma by m into e power minus gamma by m into t. And if I put x dot of 0, so if I put t equal to 0, I would get b into minus gamma by m is equal to v 0, and this implies that the constant b is equal to minus m v 0 by gamma. Hence, my solution would be a minus m v 0 by gamma into e power minus gamma by m t. So, this is a solution which incorporates one of the initial conditions, which is this. So, still we are left with one more constant, which is a here, and that can be determined provided we have one more initial condition. So, this is a sort of general technique that you could follow for any problem. In general, when you have two such constants, you need two independent conditions to determine them. And if you think about this problem a little more physically than as a mathematical problem, it tells you that the restoring force term is not there, which means that you are not going to have oscillations in the first place. And when you look at the solutions that we have obtained, either this or this, they are not oscillatory solutions. So, this is an exponentially decaying solution, so is this an exponentially decaying solution. So, in the absence of restoring force term, you are not going to get oscillation, and the solutions pretty much tally with that expectation. The last problem for this module is here. So, in this case we have the equation of damped oscillator given to us, which is y double dot plus 2 y dot plus 10 y is equal to 0, and two initial conditions are given. We simply need to write down the explicit solution. Let us start from the equation of motion for the damped oscillator. M y double dot plus gamma y dot plus s y is equal to 0, and I will divide throughout by m, so that I can make it similar to the equation that is given here. So, it will be y double dot plus gamma by m into y dot plus s by m is equal to 0. Now, when you look at this form of the equation and this equation given here, they are exactly identical, provided we make the correspondence that gamma by m is equal to 2 and s by m is equal to 10. So, before we find the solution, we need to find out in which regime we are. Are we in the heavy damping regime or in the critical damping regime, or are we in the damped oscillating regime? and that will be determined by this, by these set of parameters. The quantity of interest there is, let me call it delta, it will be gamma square by 4 m square minus s by m. So, if I substitute the numbers here, gamma by m is 2. So, this would be 4 by 4 1 minus s by m is 10. So, that is minus 9. Therefore, the quantity delta is less than 0. Hence, we should expect to see oscillatory solutions. So, it would be an oscillating solution which will be damped. So, purely from the parameters of the problem, you could determine whether you are in the regime of heavy damping, critical damping or damped oscillations. So, here we are in the regime of damped oscillations. The next step is to write the solutions. Since we are in the oscillatory regime or damped oscillatory regime, the solution that is going to be relevant for us is given here, and you will see that it has two parts to it with two constants C 1 and C 2. Now, we can plug in the numbers from the parameters of the problem, and if I do that, I should be able to write my solution as follows. Once I have written down the solution for y, I can also write the solution for y dot. I have an expression for y of t and y dot of t, and we also have two initial conditions, which is y of 0 is equal to 4 and y dot of 0 is equal to minus 4. I just need to plug these things back in these two solutions. Y of 0 will be equal to C 1 plus C 2, and according to the first initial condition, it is equal to 4. Okay. So, that follows from here, and y dot of 0 if I put in t equal to 0 in this equation, I have this expression for y dot of 0, and according to this initial condition, this is equal to minus 4. So, this straight away gives you that C 1 plus C 2 equal to 4, whereas this second condition on y dot of 0 gives you a complex number, and whereas the initial condition says that it has to be a real number, it has to be equal to minus 4. So, this would then we can equate the real parts and imaginary parts, hence it would give me minus C 1 plus C 2 equal to minus 4, which is same as the condition that we had gotten earlier, and the second one, which is 3 I into C 1 minus C 2, this is equal to 0, because there is no imaginary part in the initial condition that is given. So, this would imply that C 1 is equal to C 2, and so we just need to put let us say that C 1 is equal to C 2 and it is simply equal to C, in which case this would become 2 C equal to 4 or C is equal to 2. Hence, the constants are C 1 equal to C 2 equal to C, which is equal to 2. So, we have determined these constants. Now, all that remains is to write the solution explicitly. So, this is the explicit solution we wrote down earlier for displacement as a function of time. The undetermined constants were C 1 and C 2, and we now know that it is equal to, both are equal to 2. Hence, our explicit solution will be y of t is equal to e power minus t 2 e power 3 I t plus 2 into e power minus 3 I t. Now, you can simplify it a little more, you can take 2 outside, I will get 2 into e power minus and this suggests that multiply and divide by 2, then the quantity here is a cost function. Hence, we can write a very compact result like this. Y of t would be equal to 4 into e power minus t multiplied by cos 3 t. This would be the final result in its compact form. So, you will notice that this has the dissipative part and the oscillatory part as we expected based on the parameters that was given for this problem. So, with these 5 problems I will close this session, but I encourage you to try out the problems that is given in the assignment.